problem fixed parameter tractable. So, things like branching, kernelization, iterative compression, and some randomized techniques. These are some basic toolkit. And then we saw tree width. So, this is useful in a couple of ways. One, if you make tree width as the parameter, then we saw at least one or two examples where you can solve some problems with the real optimization problems in FPT time where the parameter is tree width. Another way we saw in particular for problems in planar graphs and so that there are you can use tree width to classify in the following way. If you have high tree width, then maybe the problem instance is easily yes or no. For example, if you have tree width more than k, then there is no vertex cover of size at most k. Things like that. So, if you have high tree width, then you can answer no or yes, and low tree width means you can apply your dynamic programming algorithm. So, this is one way in which this tree width machinery could be useful to design FPT algorithms for the parameter of your interest. So, so this could be thought of as a classification tool, right? If you want to know you have a problem which is FPT or not, you want to find out, then you just, so for example, low tree width means dynamic programming. There is a general theorem due to Kurzweil that a lot of problems which are expressible in certain logic, you have a linear time algorithm on bounded tree width graphs. So, now you have a problem, you just go and check, is it expressible in that logic? If so, you have a bounded linear time algorithm for bounded tree width graph, and then you also check if the high tree width means can you get yes or no, and then together you get an FPT algorithm. Okay, maybe a large FPT bound to the f of k, but then you start off with that and then you design some, see if any of these machineries work and design some good FPT algorithms by hand. So, today we will look at a couple of such classification tool, which sort of this, there is these big theorems. So, for example, using these big theorems, including tree grid theorem, we showed that planar vertex cover FES have 2 to the sub exponential something like this. Now, just by using some of these big tools as a black box, you could get this kind of FPT algorithm. So, today we will see a couple of such classifying tools, which per se, getting deeper into them may be hard beyond the scope of this course, but you can just use them still as a tool to design FPT algorithms. Okay. So, the two tools would be, one is this Robertson-Seymour theorem. Another is integer linear programming with fixed number of variables. We will see some examples of this. That sometimes these come handy to design FPT algorithms. Okay, so let's move towards Robertson-Seymour theorems. They were actually very deep theorems proved over a series of papers that, in a sense, founded this one of the works that started this area of parameterized complexity, I would say. Okay. So, now we are going to talk about a class of graphs, right? So, let us say F is a family of graphs. And we call it hereditary when the following happens: if G is in F and H is a subgraph of F, H is subgraph of G, then H is also an F. Okay. A family of graphs, we call it hereditary if the following happens, that if a graph is there in the class and every induced subgraph of the graph, induced subgraph, is also in that class of graphs, then such a family of graphs is hereditary. So, what do you know an example of hereditary class of graphs? K-clique free graphs. Oof. Okay, perfect graphs. Perfect graphs. Let's see why. Because if G is perfect, every induced subgraph of G is also perfect. Okay. Caudal. Why go that far? Bipartite. K-clique free. I don't know. Is it? Yes. What does I mean? What do you mean? Oh, graph with maximum click size k minus 1. Is that what you're saying? Okay, sure. So F is for a fixed k, G such that omega of G is less than or equal to k. Let's see. If a graph is maximum click at most k, then any induced subgraph has click maximum click at most k. What's an example of a graph which is not hereditary? A family which is not hereditary? Something the graph satisfies, but the induced subgraph may not satisfy. Okay, so yeah, what is the symbol for dominating set? Gamma or something, right? So let's say min dominating set. If I write this, is it hereditary? Okay. What would be okay? So give me an example graph which has a take a star graph which has take a star graph, star of whatever that degree k, right? Or k plus 1. This graph has a dominating set of size even 1. But if you look at the induced subgraph on this, that doesn't have such a dominating set. Okay, so this is not hereditary. Connectivity is another property, simple property. If I take the collection of all connected graphs, a graph may be connected, but here's an example. Here the graph is connected, but if I pick these some 3 vertices, they don't induce a connected subgraph. Right? So, F is graph, number of components of G is 1. This is not hereditary. Okay, now what do we know about hereditary graphs? So, okay, let's talk about, there is this notion of forbidden set, right? F for this family so F is a family of graphs, and my forbidden, and it's family of hereditary graphs, and the forbidden set is G such that G is not in F and G is minimal, in the sense that every subgraph of G is in F. Oh, yeah, bipartite. Right. So, for example, if I take if F is the collection of all bipartite graphs, then what would be this forbidden set? Right. If F is a family of all bipartite graphs, then what is the forbidden set? It's just collection of all odd cycles. Take an odd cycle because that is not in F, and if you take any subgraph of it, it will be there. Right. So, basically you take collection all graphs which are not there and just pick the minimal subgraphs. That's a forbidden set, right? So, this is called a forbidden set. Then it's easy just by definition that G is not in F if and only if there exists a H in the forbidden set such that H is a subgraph of, H is an induced subgraph of G. Actually, I should say every induced subgraph. So, H is not in my family. When is it? I mean, clearly, if there is some H, so one direction is easy, right? So, this is a nice little theorem, and just I've defined FFF, the forbidden set, in a way that this theorem is true, more or less. Okay. So, here is my G, and there is some H sitting inside, which is not in the family, or it is in the forbidden set, which means it is not in the family, then clearly G cannot be in the family, because G is F is a hereditary family. If G is in the family, every induced subgraph must be, so H should also be. Since H is not, G is not. So, if there is some H such that H is an induced subgraph, then G is not in F, and conversely, if G is not in F, it must be in this forbidden set, unless it is not minimal, right. So, that means that if it is not minimal, means that you can just pull out a minimal subgraph from G, which will be in F. So, there exists an H such that H is in the forbidden set. Okay, this is a nice little theorem. Now, what's a corollary of it? Suppose this forbidden set for this class is a finite set. Okay. Oh, for example, cluster graph. Cluster graph means it's a collection, it's a disjoint union of cliques. It's a collection of cliques. Every component is a clique. Any such graph is hereditary, because if you take a an induced subgraph, it's again collection of cliques. And what is the forbidden subgraph for a cluster graph? We saw it is a P3, only one graph, right? That is for the class of bipartite graphs, the forbidden thing is all odd cycles. It's an infinite family. But for the class of cluster graphs, the forbidden set is one graph, P3, right? So similarly, for example, split graphs have a finite forbidden set. I mean, I could just have a collection of forests. That's another hereditary class, right? Collection of graphs, which each one is a forest. What is the forbidden subgraph for that? All cycles, right? Again, it's infinite. So what I'm saying is, suppose the forbidden set for a class is finite, then we can test whether a given graph so given a graph G, I want to know, first of all, I should, okay, to address this question, you should ask me how is the family given, okay. Well, class of all bipartite graphs, okay. So it's given as it is. So now I want to test, okay, it's given as some sort of a property in constant size or something. Now I want to test, somebody has given me a graph and I want to know whether it belongs to this class or not. Is it bipartite? Is it connected? Is connected is not hereditary? Is it perfect? Is it caudal? Is it a cluster graph, right? Is there a polynomial time algorithm for this problem, right? Given a graph, does it belong to this class? What I am saying is, suppose somebody has a finite forbidden set for this class, then there is an easy polynomial time algorithm. What is the easy polynomial time algorithm? This theorem gives you a way to do it. What do I have to do? To test whether G is in F, all I have to do is there a H in the forbidden set which is an induced subgraph of G, right? Now, the forbidden set is finite. I go to the forbidden set, pick one graph and check, okay, is this a subgraph of my original graph, right? How do I check it? Well, try all possible subsets of this size, okay. The important thing is, when I say finite, okay, so let's see, what is the, so I have this family and somebody has given me this finite forbidden set for this family, right? So now given, so now this is, these sets, these graphs are properties of the family, right? It has nothing to do with your given graph, right? Nothing, because I haven't even given you a graph, you have given this family, right? It is just a function of this family. So I can, the largest size of HL, any of these graphs may be some then what do I do? Given my graph G, I want to know whether it belongs to this family. Then by that theorem, I want to know whether any of these subgraphs, any of these graphs is a subgraph of this, right? So I, for example, one naive way would be to try all possible subsets of size at most D, some n to the D time, and I pick this thing and check whether, does H1 belong to this? Is H1 a subgraph of it? You can do isomorphism, try all subgraphs here, all kinds of things you can do because D is a constant. D has nothing to do with your input. D is just a constant. For example, for cluster graph, that D is like 3. Okay? So, D is 3, 10, 15, whatever. So, you check whether this is a subgraph, this is a subgraph of my G, try that for every H, and if none of this is an induced subgraph of G, then by this theorem that G belongs to the family. So, I have a polynomial time algorithm if this is a finite set. Okay. Now, let us come to parameterized complexity question. So, now what do I want to know? So, given again some f and parameter k, what are the question I would be interested in? Input is G and k, let us say. The question is, does there exist a subset of vertex set whose size is at most k such that G minus S is in the family? Right? Given a graph, okay, it may not be in the family, but can I delete k vertices so that it belongs to the family? Right? We have seen throughout a lot of examples, right? If F is a family of forests, then what is this problem? Feedback vertex set, right? Can I delete k vertices so that the graph becomes a forest? We've seen that. If F is a family of bipartite graphs, then this is exactly the odd cycle transversal problem, right? So, we have seen these questions. Now, so even here, is there an FPT algorithm for I think this was in your assignment in the okay. So, now theorem. Suppose the forbidden set is finite, then the above question is FPT. Remember how we did this? But that's like an n choose k. It's not FPT because you're deleting k vertices. That's an n to the k algorithm. Yes, so that's one that shows that it's an XP. That try all subsets, delete it, and then I know apply that algorithm in the remaining graph. Does it belong to that graph? That's n choose k. How do I get an FPT algorithm? Recall what we did for cluster vertex deletion because it's exactly that, right? Cluster vertex deletion. Yeah. So what? Yeah, branching is a good start, but give me a precise solution. Pick a member of the forbidden set which is a subgraph of G, right. So, this n to the D algorithm I will do. I go to my G and check whether any of this H is a subgraph of G, right. If not, great, G itself is in my family, no problem. I do not even have to delete any k vertices, right. If I find some subgraph, some one of these forbidden subgraphs sitting inside G, then what do? I have to delete one of them branch. So, that gives me like a d power k algorithm, right, d way branching because d is the maximum size. So, I will do this n to the d kind of a thing, find some hi which is inside G. If none of this is inside G, G itself is in my class and I am done. If not, I will find one of these hi and say, okay, here is this forbidden subgraph I need to delete one of these vertices. So, I will try one at a time. That gives me a deep k algorithm, branching algorithm. Okay, this is how we did cluster vertex deletion, vertex coverage like this, right? What is F? So that this is edgeless graphs. Collection of all edgeless graphs is F. Then what I am asking, can I delete k vertices so that it becomes? So what do? I go to my forbidden set. What is the forbidden set for such a F? An edge, a graph with one edge. So the moment I find an edge, I know that one of the endpoints has to be deleted. So this was the branching algorithm exercise in your assignment. So this we know. Now, if it is infinite, we don't know a general theorem. This is open, right? Because we have these examples of bipartite, OCT, FVS, which are FPT, which are exactly classes of graphs which have infinite number of graphs in the forbidden set, for which we know specifically there is FPT, but we don't have any general theorem about when it's FPT, when it's not. Okay, it will be nice to have such a dichotomy theorem. Another version of the parameterized question we can ask is, given f and input g k, does there exist an S contained in Vj such that I would say S is equal to k, and not G minus S, but the induced subgraph on S is an F. Okay. So, is there a k, given a graph, is there a k size subgraph that induce a graph in the class, right? So, for example, if F is the family of again edgeless graphs, then what is this problem? Independent set problem, for which we know is W1 hat. Right? I could also pick F as the family of cliques, then this is a clique problem. And you can take your F and say, is there a cluster graph of size k? Is there a forest? Are there k vertices that induce a forest? That's another interesting set of questions in the parameterized world, for which there is a very nice dichotomy theorem. We know we have a theorem FPT. I don't know whether we did this sometime in the class. Okay, so I'll give you FPT if F contains, or let me see. All cliques but not all independent sets, or vice versa, and FPT otherwise. So F is this family of graphs. If my family contains all cliques but not all independent sets, or it contains all independent sets but not all cliques, then it's W1 complete. Finding a k-sized induced subgraph of that property is W1 complete, and otherwise it's FPT. So let's pick, for example, if F is a family of all chordal graphs, right? If F, let me write some. And what category it belongs to? Then what is this question? The question is, given an arbitrary graph, are there k vertices that induce a chordal graph? Okay, can you find some k vertices in this graph that induce a chordal subgraph of the graph? Now, so now this is a template, you can plug it in. So F contains all cliques are chordal. Any clique is a chordal graph. Any independent set is a chordal graph. So, F contains all cliques and all independent sets, right. So, it does not belong here, so it is FPT. But if you ask, so it is FPT. But if I ask you if F is a family of Forus, then all independent sets are Forus, but all cliques are not. Some cliques are Forus, right? A clique on two edges, two vertices, one edge. So, it includes all independent sets, but not all cliques. So, it belongs here. So, it is W1 hat.
Does this not imply that it is anything is W1 complete or
Yeah, it is. That's the nice thing. If you have a hereditary class of graphs, then there is a clean dichotomy theorem. All I said is for the deletion question, where can you delete k vertices to get into F, we do not have such a nice theorem. We know that if it is finite, it is FPT. If it is infinite, we have some examples where it is FPT, we have some examples where it is W hard as well, but we do not have a nice theorem like this. Okay, so let me just give you why this is true. I mean, both of these really use nice Ramsey theorem very nicely. So, here it is. What do I know? All cliques are chordal, all independent sets are chordal, right? So, if the graph has a large number of vertices, we will figure out what large is. It should have a clique on k vertices or an independent set on k vertices, right? Okay, I am saying too many things, so let's just want to take stock and make sure you are following what's going on, right? So this is a general theorem. I am not going to give a proof of this, but I will give you a flavor of the proof at least for one direction, right? If the family contains all cliques and independent sets, I will say it is FPT. Okay, but otherwise its W hard implies a I mean, this is done using some reduction from clique or independent set. Okay, so given G, if it has more than this Ramsey number, then G has a clique or an independent set on k vertices, right? That is the definition of RK. If you have not seen what this Ramsey number is, it is the definition of that. What is the minimum number of vertices in a graph we should have, so that you can talk about Rij. What is the minimum number of vertices? Let us call that number as Rij, such that any graph on that many vertices will have a clique on I vertices or an independent set on j vertices. That is RKK, and there are bounds for this known. Okay, so that is it. We are done, right? So which means that G has a chordal subgraph on k vertices, because cliques are chordal, independent set of chordal. So if otherwise, number of vertices is bounded by a function of k, brute force. You have actually a kernel in some sense, right? So And all we really use the fact that every clique and every independent set is a chordal graph. So that's one part of this theorem, that if your family contains all cliques on are all independent sets, then this question is FPT. Okay, good. Now I still haven't come to Robertson-Seymour theorem. It's all for towards that. Okay, so these are some on the hereditary graphs. When we are talking about family which is closed under induced subgraphs, we have some general theorems. We have some open questions. We have studied about can you delete k vertices to get to that class, and all that is fine. Now let's talk about minor closed family of graphs. Okay, so these hereditary graphs are closed under induced subgraphs. Now a minor closed family is so my family of graphs F is minor closed if following happens: G is in F, H is a minor of G, implies H is in F. And I recall what a minor is: graph obtained from G by deletion of vertices or edges or contraction of edges. So more or less a lot of graphs we've seen are bipartite graphs. No, they're not. Bipartite graphs are not because you can create an odd cycle. Like suppose you have an even cycle. Yeah, or
But they have a forbidden minor.
no, wait. Yeah, I mean, you have this is a bipartite graph, but I could contract this H, and what do I get? I get this, right? So G is in the family, H is a minor of G, but H is not in F. So bipartite graphs are not, right? So examples of minor closed and not would be bipartite. And here for us, for example, by contracting an edge, you want to create a cycle. Bounded tree with graphs we saw. Planar graphs. Planar graphs are also hereditary, but they're also take a minor, you want to create non-planar. But here also graphs with vertex cover at most k, like tree width, for example. If you have small vertex cover, by taking a subgraph and by contracting edges, the vertex cover size is not going to go up. Similarly, feedback vertex set. These are all minor closed families of graphs. Now, this famous theorem of Robertson-Seymour is the following. If F is minor closed, then F has a finite forbidden set where, so I mean this is something we wanted it for hereditary graphs, and I said we don't. For example, the class of bipartite graphs is an infinite forbidden set. But what Robertson-Seymour showed is that if your graph, the family of graphs is minor closed, that means if you have a minor, it should also be inside, then it has a finite forbidden set. But here, what do you mean by forbidden set? In the hereditary case, it was just induced subgraphs. Here, you are looking at minors. So my forbidden set may have H1, H2, some HL. Then G is not in F, F1 only if there exists H in F such that H is a minor of G. So they showed this, that if it's a minor closed family, then there is a finite forbidden minor set. Now, one question is, how do I check whether H is a subgraph of G? I sort of glossed over it. So what you do is you look at all subsets of this many vertices from G and look at that graph, induced subgraph, and see whether H and that induced subgraph are isomorphic. Okay. How do you check for isomorphism? Well, I don't care. Run through all possible permutations of the vertices and check. Right? We don't right now. We don't have a polynomial time algorithm to check whether two graphs are isomorphic, but you don't need it because I'm just talking about, if H is small size. Remember, in the forbidden subgraph characterization, the size of this forbidden sets are constants. So this is a constant. So you run through all permutations and then you do this check, right? So that means it's n choose H was the thing. But checking for minor is a lot more complicated because it's not just about induced subgraph. You could have gotten it through a lot of contraction, but they also showed. So this is theorem 1. Their second theorem is that given H in G, we can test whether H is a minor of G in order some size of G cubed time where the constant is some function of H. Okay, so you want to know, here is this graph and I have this H which is sitting there. I want to know H is a minor of G. Then they also gave an algorithm which can do it in n cube time if n is the number of vertices in G, where this constant, so there is a constant which is a terrible function of the number of vertices of H. Okay. So now I claim that these two theorems give you a way of coming up with an FPT algorithm for problems. Okay, it's a very big classification tool. How is that? So, let us look at FES, right, and K, and the question is, does G have an FES of size at most K? Right? We have seen a lot of FPT algorithm, but I am going to give you how to give an FPT algorithm using these two theorems. So, let me define this family of K, all G such that G has an FES of size at most K. Right? And since I have listed down here and we checked, this is a minor closed family, because if a graph has K vertices whose removal makes it a forest, then if you take any minor of it, then it will also have. Okay, this requires some argument. All you have to do is that when you delete a vertex or delete an edge or contract an edge, the FES size does not go up. So, Fk is minor closed. So, by Robertson-Seymour theorem, there exists a finite forbidden set. So, now what is my question? What is this question? This question is the same as, given a graph G, does it belong to this class? That is what I am asking, right. Now, this tells you that G belongs to this class if and only if none of this set graph in the finite forbidden set is a minor of that graph. Well, take one by one and check whether it is a minor, and I have an n cubed algorithm for checking whether it is a minor, one H is a minor of G, right. So, for each H in F, check if any of them is, return no, else return. That's it. That's an FPT algorithm. Why is it an FPT algorithm? Let's see how much time have we spent. Size of the forbidden minor set, that just depends only on K, because until you created a H, I did not even bring my G, right. It just depended only on K. So, the size of the forbidden minor is a function of K, the number of graphs, the number of vertices in the graph, and all of them are a function of K, and then checking whether this is a minor of G is only an n cubed time algorithm because of that. So, it is n cubed times a huge function of K. But again, it is a nice classification tool, because the only thing you need to know is whether the class of the S instances is minor closed. So, you just write down your class of S instances, go and check if G belongs to, and if H is a minor of G, does it belong to this. Okay. Again, it is a classification. Okay, so now there are a lot of problems. One is that this theorem is non-constructive. They do not give you a finite forbidden set, they just say that there exists a finite forbidden set. The second problem is that this f of h, also the size of this forbidden set is huge, like a tower of exponents and various things. So, similarly, this f of h is huge. So, this is, I mean, there is a problem that I may not even have an algorithm, because I do not even know how to get my f. Secondly, even if I have an algorithm, that algorithm has a terrible f of k, but it is a classification tool. You can again quickly check before you start proving it is W hard, you fit it in here, and if it is, then maybe using one of those efficient techniques, you may be able to come up with an FPT. Okay. So, in that sense, these two theorems sort of builds from hereditary graphs, takes you to the minor family, but they have this nice little theorems which are useful to give FPT algorithms for problems, at least very complicated or very bad FPT algorithm, not complicated because you just if you use them as a black box, you can just get immediately, but the FPT bounds may be bad. Okay, so this is one important classification tool I want to talk about. Then I move on to the next one, the integer linear programming. So any questions or comments?
Are there theorems like this covering larger or
Yeah. No, not Corsair. If you're talking about these Robertson-Seymour types, then yes, there is for a lot of structures, not just graphs, trees, there are Robertson-Seymour type theorems for some different classes of objects.
no? I meant like this condition that minor here, the class has to be minor close. Some other condition.
Right. Okay. So there is this topological minor for which the problem was open and it was shown few years ago. So you allow only edge contraction, I think, or something like that, and that's called a topological minor. And you talk about deciding whether H is a topological minor of G and things like that. Okay, the next big tool which we are going to use is the following. So, integer linear program. So, we know that linear programming can be solved in polynomial time. In fact, we use that to design some FPT algorithm, approximation algorithms. Many optimization problems can be modeled as an integer linear program. Hence, integer linear programming is NP hard. You can't solve it in polynomial time. But what we know is that suppose the number of variables in the linear program is bounded. Okay, your linear program has, what integer linear program has, there is an objective function, there is a minimize summation Ci xi, and then there is a constraint, and then so this is how a typical, instead of min it could be max and less than or equal to. This is how a typical LP looks like this. Now with this integrality constraint, you have an integer linear program. So let me just write down the theorem. ILP with p variables. So if this xn next to xn or p variables can be solved. Okay, if you know enough about LP, basically what a basic, if there are p variables, a basic feasible solution would be a solution to p constraints. So if there are n constraints, you try all possible p constraints and choose p many constraints, solve the equations, and you get these points, and one of them is the corner point. Okay, you can try minimizing and so on. So it's like an n choose p kind of a constraint, n choose p algorithm. But what we know is that if it is fixed parameter tractable with respect to p, the number of variables can be solved in p power order p times some poly in this is the length of the instance. Okay, I mean, to describe this entire LP, I have to write down these coefficients. I have to write the coefficients of the constraints, and write them all in binary. And you have this. Let's call that as the length of the input. Basically, there is a p power order p times some polynomial in the length of the constraints, length of the rest of the thing input. Okay, so let me just write more precisely. Okay, so more precisely, let me write this as so. This will be like L plus log mx into log mx mc where this is the max value of a variable and this is the max value of a coefficient. But the real important point is that somehow you are looking at a parameterized problem. There is an input, there is a k, and you want to design an FPT algorithm. If you can model it as an integer linear program, usually you can, because many hard problems can be modeled as integer linear program with some function of k many variables, then you have an FPT algorithm. You make sure that the number of variables does not depend on your input n, but just depends only on some function of k, and write down your integer linear program. Then you can apply this. If the number of variables is some function of k, then this is the real exponential part. The rest of it is some polynomial. And this is just saying that a variable can take some at most some polynomial value, and the coefficient is of something at most some polynomial, which will typically be the case. Okay, so we'll run it on an example. Now, does this make? I mean, vertex cover, for example, can be written as an integer linear program. Number of variables is like n. Okay, so fine. This just says that there is an n power n output, so it doesn't make p equal to np or any such thing. And many of these tools are really, very useful when you're working on research. So, and we have people who have written papers using these tools, so it's good to know them. Okay. So let's run it on this problem. This problem is called imbalance. So what is the problem? You have given input G. What we want is some ordering of the vertices. Let's call it V1, V2, Vn. Let's define di for vertex I to be neighborhood of Vi intersection V1 to Vi minus 1. Okay, let's call this L of I, and R of I to be neighborhood of Vi intersection Pi plus 1 to Vn and d of I to be Li minus Ri, and this notion of imbalance summation di equal to 1 to n imbalance is minimized. Okay, so for every vertex, this is size. I look at the number of neighbors to its left, that is Li, L for left, number of vertices to the right, take the difference. No, for some reason it's defined as Li minus Ri, and you want to minimize this imbalance. Actually, it is more. Okay, I guess it doesn't matter. So it is mod, yeah. So you want basically, as many vertices in the left as many vertices in the right if possible, then imbalance would be like 0. You want an ordering that minimizes this. And it's like an embedding problem. I have this graph and I want to embed it in a line or something like that, and basically, yeah. So given a graph, is the imbalance less than or equal to k is one question, which is FPT, and that is not the problem we are going to look at. We are going to look at slightly different problem with vertex cover So this belongs to the structural parameterization I talked earlier on about, right? Your input is not very far from an independent set. Our input is not very far from a tree. So for the most part of the course, the parameter was our solution size, but more natural parameters is how there's something in the input. So in particular, I'm saying that you have a graph which has a vertex cover of size k, and that k is the parameter. I want to find an ordering of the vertices that minimizes the imbalance. Okay. So it's a minimization problem. So I will eventually write it as an integer linear program with some constraints. But the number of variables I will come up with would be some function of k. Okay. So how does the graph look like? So here is a vertex cover, right? There may be edges here, but this is independent. And I want an ordering of the vertices which minimizes the imbalance. So I am looking for some ordering. So now, one is we will come up with a function of k many variables and model this an integer linear program. Other thing is that we can sacrifice k interestingly, right? So first thing is, among all orders of this vertex set, or for every order of the entire vertex set, there is an order of the vertices in the vertex cover, right? So, there are only k factorial many orderings of the vertex cover. So, let me just guess the correct ordering for the vertex cover by running through all possible k factorial choices. Okay, that is a k factorial. I will. So, in other words, I have to place every vertex somewhere. So, let first assume that these vertices are relatively correctly fixed, and I have to pay a cost of k factorial for that, right. Okay, so let S is equal to V1, V2, K, and be the optimal order otherwise I am going to try, right, k factorial orders. The point is, once I fix this order, there are a lot of structure to the problem. All I am left with is to where do I put the remaining vertices, and I have some handle on coming up with some function of k different types of vertices. So, now so there is V1, V2, Vk, and then I have my remaining vertices which I have to place, right. Let us make some observations. So, I claim for, so this is V minus S, let us make some if V and W in V minus S fall in the interval, let us call it x and y, in the interval Vi minus 1 and Vi. So, I have to now decide where do I want to put these vertices, and these vertices go, there are k plus 1 intervals where this can go, right. My first observation is that if I decide how many vertices go into this, among them it does not matter how they are placed, because this is an independent set, there are no edges, they are not contributing to the imbalance on these. So, if I put suppose I decided that x and y belong here, x and y are some two vertices here, for some reason I decided that both x and y go here in this interval or some interval, then it does not matter whether I put x before y or y before x, the imbalances will be the same, because these guys are independent. The imbalance is caused by its connections to what is before and what is after among the Vi's. Okay, so that's, so now what do I have to need to know is, okay, then does not matter the inner order does not matter. So, we really need to know which set of vertices of V minus S belong to an interval. Okay. So, our problem boils down to, from here tell me which set of vertices belong to this interval, which belong here, which belong here. That is one thing. Second thing, suppose two vertices have the same neighborhood there among the VI's. The neighborhoods are only out there anyway, right. Suppose two vertices have the same neighborhood here, then so let us say there are 10 vertices which have the same neighborhood. Okay. There are 10 vertices from here which have the same neighborhood, and somehow in my optimal solution I figured out that 3 of them belong here. All right. So, let us define this, right. Neighborhood type, vertex V in V minus S is of type X contained in S if n of x is equal to x. So, now I am going to talk about, for every vertex there is a type. Every vertex here there is a type which depends, which is basically what is its neighborhood. If n of v is a particular x, then vertex v is of type x. How many types are there? Good, right? That's another function of k. So, number of types is, now I am just sort of trying to come up with some equivalence class. I am just saying if there are 10 vertices of the same type, in my optimum solution I decided 3 of them belong to this interval. Does it matter which 3 belong here? No, because they have the same neighborhood, and the imbalance is caused by, among them there is no problem, how many of which type, how many to the left, how many to the right. So, if for my optimal thing I decided some 5 vertices belong here, 5 of a particular type belong here, it does not matter which 5. You agree? So, now my question boils down to, among the 2 power k type vertices here, for a particular vertex of a particular type, how many belong to each interval? That is my question, and so I am going to create a variable for it. So, a variable let us call n x okay NIS S NIX. X is contained in S, and that is my vertex cover, and I is between 0 to k is the number of vertices of type X that belong to interval Vi plus 1. Now we are done once I define this. So, all I have said is, from these observations which I did not really completely write properly, I am saying I have my graph. I have fixed an optimal ordering for the vertex cover set V1 to Vk. I have to now place these guys in any of these intervals, right. So, what do I care? I really care about how many vertices of a particular type that go into this interval, how many of this of the same type that go here, here, and so on. So, Ni of x is the number of vertices of type x that go into the interval Vi plus 1. Let us define that variable. Now, I am going to, what do I want to minimize and what are the constraints? We need to write it down and be done. Okay. So, the final order, I am just saying that this is an optimal order. The final ordering of the entire vertex set can be characterized by, for each type of vertices, how many belong to a particular interval. If you tell me that, that's good enough, because I don't care which of those many vertices go here. I just pick some of them, put them. I don't care what order they are. And that's it. They fit in there. Once I do that, and then I get an ordering for the entire vertex set. So now let's talk about what is a constraint. So how many variables are there? There are k into 2 power k, or k plus 1 into 2 power k is the number of variables. The constraint is that I can't get, can I get too many of them into a particular interval? What constrains me?
Has to be less than or equal to n.
Less than or equal to n. Okay. So let's say, first of all, let me define n of x, number of vertices of type x. Right? From here, I look at their neighborhood. Okay. For this particular neighborhood, these 5 vertices belong to this particular neighborhood. Another 10 will belong to another type. So for a particular x, let's write down the number of vertices of type x. Then the constraint is that summation ni of x, where I going from 0 to k, better be n of x. This is essentially the only constraint, because you are saying, oh, of this type, 3 belong to the first interval, 7 belong to the second interval, 23 belong to the third interval. Let their sum be the total number of vertices of that type. That's all. Don't go beyond that. You just have to distribute them. That's the only constraint. For every vertex, every type vertex, there are so many here at the bottom. We can compute this n of x. Just make sure that they are distributed in these k intervals. That's it. So now let's compute our imbalance and write the minimization question. Right? What is the imbalance? Right? The imbalance. There is imbalance with respect to every vertex here, and then there is imbalance with respect to every vertex here. So let's write that down. For every v minus s, what is its imbalance, right? Or it's better to write it for every type. Right, okay. So for every v in type x, what is its imbalance, right? Well, they are all distributed. Some are in the first interval, some are in the second interval, some are in the kth interval. So based on that, you will have an among them there is no problem anyway. You only care about the things outside. So is there a nice formula which I can write it down? Okay, so ni of x, or okay, this many vertices go into the interval vi to vi plus 1, right? So here is vi, here is vi plus 1, and number of vertices that go here is ni of x. What is the imbalance caused by them, right? Well, x is their neighborhood. Remember, vertex, any vertex here is defined by this its neighborhood x. So for each one of them, it is x intersection V1 to Vi minus x intersection Vi plus 1 to Vi. So, all vertices of type X cause this much imbalance, and then I run over all okay. It looks humongous, but once you understand this definition of NIX, what is it saying? Yeah, look at this interval Ni of X of, so that means so many vertices of type X get into this interval, and so they are all going to cause, each one is going to cause me some imbalance. What is the imbalance they cause? Well, their neighborhood of X, and how many of the X's are here, that is the left side, X intersection V1 to Vi, minus how many of their intersections are here, and all of them have the same intersection, same neighborhood. So, Ni of X, all of them are going to cause this kind of an imbalance for me, and run this over for every I and run this over every X, and that is the imbalance caused by vertices below, the B minus S. What about the vertices above? They also cause imbalance. So, minimize, that is my objective function, right. This is the imbalance, this is the constraint. Okay, vertices above, what is the, so let us pick some Vi here. What is the imbalance it causes? Well, what is the neighborhood here minus this neighborhood is one imbalance. Plus some more. Plus to all the vertices that belong here also, right. So, summation I equal to 0 to k, some, let me write this as imbalance caused by that vertex. What is this imbalance caused by that vertex I?
Now you're looking at the imbalance caused by the E1 to Vk vertices.
Right.
But you can pre-compute, right? I mean, when you
among them, yeah. I mean, among them I can pre-compute them, but they also cause, there are some vertices here that go before this, so that is also an imbalance, right. So some of them I can pre-compute. One of them is this, that neighborhood of Vi intersection V1 to Vi minus 1 minus neighborhood of Vi intersection Vi plus 1 to Vn is one set of imbalances among themselves, plus okay. So, look at all, summation over all X that contains Vi. That means for those types of vertices also, because they are all neighbors of Vi, they are going to contribute to them. And how many of them is basic, what is the imbalance caused by them is how many of the types of X. hope it's correct, and I really wrote it without looking up. So for any vertex here, so we counted the imbalance caused by the vertices here among, that's this. There are no edges among them, so these guys are causing imbalance only with these vertices. Now for every Vi here, first look at its neighborhood here to the left minus the right, that is one sort of imbalance, that is the first term here I wrote down. The second term is that look at all sets that contain Vi, okay, all types X that contain Vi, because those are exactly the neighbors of Vi, right? Among them, all those types, how many have come before me and how many have come after me, I subtract them, right? So Nj of X is the number of vertices of type X that is in the interval J. So for every X that contains Vi, I have to look at this and subtract it. Net, we have formulated the problem. It just boils down to, there are these 2 power k types of vertices, right? The number of vertices is like n minus k, but really they are of only 2 power k equivalence classes, and I have to place them in the k intervals. How many of each type goes in which interval is what I really care. That is this variable, and once you fix that and that specific, and then you can compute this imbalance based only on this number of variables, and the total number of variables is k plus 1 into 2 power k. So it's a function of k. You can plug it into that theorem I wrote down and get an FPT out. Yep. Okay, so the whole problem is to minimize this subject to this constraint. Okay, so this is another tool, integer linear programming with finite number of variables to classify something FPT.